This actually work was done here by one of our previous graduate students, Arthur Choi. He did his PhD thesis on it. So what happens is the very first version of this looked very similar to what we just talked about and started generalizing. And year after year of understanding and so on, we found the most abstract way of describing what's going on, leading to this framework called relax, compensate, then recover. So let's go over it. And let me just tell you one thing before we start. So the whole point here is to try to give semantics to things. People talk about good semantics and not so good semantics. Semantics, in a way, meaning. You know, I show you something and I give you insights into it. The extent to which the semantics are good or not are usually measured by what does the semantics allow you to do that you couldn't do, right? So if I come and tell you, look, I'm going to give you some insights into this algorithm, and then you want to evaluate how valuable is what I told you. One way to look at this is, what can I do now because of the understanding you gave me that I couldn't do before? And you're going to see this here, right? You're going to see that the semantics of what I'm going to show you next is will enable people to play this game of trading off time with. So here's the theme. The theme is, again, this is going to look like completely disconnected from what we've done, but as we move on, we're going to find that what we did is a special case. Approximate inference can be viewed as exact inference, but on an approximate model. And how do I get this approximate model? By relaxing and compensating for equivalence constraints or equalities. I'm going to explain this now. You give me a network. You want to do exact inference on it. Its Treewidth is very high. I can't do it. Then look what we can do. And in this part, we're doing one more generalization. We talked so far only about Bayesian networks, and I told you there are other types of graphical models that are undirected. We're going to do the treatment in one of them, so we're actually doing two things here. How many heard of Markov networks? Markov network, you know, random fields, pairwise MRFs. It's very simple. This is called a pairwise MRF. It is a special case of this creature. It's a graph, and it's very simple. With pairwise MRFs, what you do is you have factors over edges. So these are variables, right? So when you put a factor here, the factor is over two variables. Or you put a factor over individual variables. Looks like this. So what is the distribution that's specified by a pairwise MRF like this guy? You just multiply all of the factors, just like we do in a Bayesian network, right? These are the factors over individual variables. These are the factors over edges. The only thing here, though, is there's no guarantee that this will be normalized. In a Bayesian network, you're guaranteed because the factors have a specific meaning. They are conditional probability distributions, they're CPTs. So when you multiply them, you get a normalized guy. Not here. So what do? You normalize. This Z is the normalization constant. This Z is a very important number. It's called the partition function, right? You can write it. It's just taking this guy and doing what? Summing it for all possible values of the x's, correct? That's the partition function, this guy. We're going to come to it. So this is the distribution induced by that. Straightforward, okay? Everything else is the same. Now, look at this technique of approximating a model by relaxing equivalence constraints or equalities. And as you will see it, you can use this model, this technique, to take any model and control the Treewidth. That is, you can reduce the Treewidth as much as you want. Let's first see what is an equivalence constraint or equality constraint. You have two variables, xi and xj, over the same values. It's a factor. An equivalence constraint is just a factor that says when for the row and the factor where the two variables have the same value, it's a 1, otherwise it's 0. Does that make sense? This is basically the factor over these two variables. Let's say these are binary, then there would be 4 rows in this guy, correct? And 2 of them will have a 1, and 2 will have a 0. That's an equivalence constraint. Now look what you can do. Here's a model. Let's say this is too complicated. I can't do exact inference on it. So I want to do something to it. So I can do simplify it and do exact inference on it. Look what we're going to do. See the animation. What did I do? For a bunch of variables, this guy was C, right? What did I do? I created a clone. So now I called it C1 and I created a guy called C2, right? And then what did I put on this edge? An equivalence constraint. That they're the same variable. I didn't do anything. I didn't change the model. You guys see that? And similarly here, this was E. I made it E1, E2, and put an equivalence constraint, equivalence constraint, equivalence constraint. You're with me? I didn't change the model. It's hairier now, has more auxiliary variables, but it's the same model. Okay. Now, the idea is I want to use only one tool to simplify a model, which is dropping equivalence constraint. If we drop the equivalence constraints here, look what happens. I got now a 3. Treewidth is 1. Here's how it was. And now look what I did. This is now what we call relaxing equivalence constraints. You can see with this trick, you can take a model and make it look any way you want as far as its connectivity. Okay? But this is the catch here. You'll see now in just a second. This is just another concrete example. Here's the model. Look what I did here. Did it differently. So C1, C2, E1, E2, and if I drop, what did I do? I split it into 2 parts. Okay? In what way is this approximate compared to the original one? It have forgotten about the fact that C1 and C2 are the same variable. You guys see that? It's ignoring that fact. That's problematic. Okay? But I will do something to it that improve it, and you'll see in just a second. So here's the big picture. Look what's going to happen. You're going to start with the model. You're going to relax some of, add auxiliary constraints, relax some of them. When you do this, you have dropped some equality constraints. So that's pretty bad model. I'm going to try to improve it by doing something called the compensation step. The compensation step is, you'll see, I will adjust some of the factors on this guy to make it as closer to this in a certain way, in a certain sense, right? And there is a third step we'll talk about later called recover. But let's look at how do you actually compensate. Look how interesting this is. What did I do when I dropped the equivalence constraint between xi and xj? I'm forgetting, erasing the fact that they are the same variable, equal. So what I'm going to do is, I'm going to try to enforce a weaker notion of equality. What is that weaker notion? They have the same probability. You can do that by adding these auxiliary factors and choosing their values carefully. So these are not part of the original model. I have to add these and choose their values carefully so that the probability distribution over that and this are the same. So I will drop an equivalence constraint. I will add auxiliary parameters to my model and see if I can find values for these so that the now compensated model will find this guy and that guy having the same distribution. It's not the same as equality, but it is same distribution or probability. You're going to see that actually that's what iterative propagation is doing. Okay, the question is, I'm going to tell you, wait a minute, how do you find these guys? How do you find these? So that if you plug them in, these are the compensations, then you will get that. I'll show you now the update equations, which actually turns out to correspond to what belief propagation is doing. Here's the equations. Here's the update equations. We talked about z. Z is the partition function. You guys know about partial derivatives, right? You've seen them before. So this is, you can think of it also as a polynomial, right? So the partial derivative of the partition function with respect to this auxiliary parameter, I want it to be equal to the value of the auxiliary parameter. If you reach this, then you get that. So my goal is to find these guys so that I satisfy these equations. If I do, then I have enforced a weaker notion of equivalence. And how do you do that? This is an iterative equation, right? You start by guessing these parameters first, and then you apply the update equations, right? How do you compute the derivative? We've seen. I mean, it's not a big deal. once more, you go ahead and guess these guys initially, and then you apply these equations, and you converge when this equals that. Then you get that in that particular case. So this we've done relax, then compensate. Now we're going to see the implications of this picture. The first one is the correspondence to belief propagation. If you take a guy like this, and you delete every edge, get something like that. Now what are you going to have? You're going to have a compensation on this and a compensation on that. Compensation here, correct? What's going to happen when you find these compensations? Start iteration 0, you initialize them. Iteration 1, you compute the new values for these. What are you computing? You're computing a factor over a variable, right? This is what we had here. Let me go back. This guy. You're doing it for this guy, you're doing it for that guy. Okay, look. Now, iteration 1, iteration 2, iteration 3, you converge, then you have that. All right? And then you have the compensation. Those compensations that are being computed happens to be precisely the messages passed by iterative belief propagation during iterations. That is, you can look at belief propagation when it's running on this guy, and you can look at these messages, and they correspond to those compensations that we mentioned. That's what it's passing. It is doing exactly what we discussed. The interesting thing is, you get that if you delete every edge, but you also get the same thing if you only delete enough edges to get a tree, connect a tree, any tree. You will still get the same approximations. Where does this get interesting? Then you're telling me, wait a minute. So this is belief propagation. Iterative belief propagation, what is it doing? It's deleting every edge or deleting every to get a tree. Why do I have to do that? Why do I have to do that much? Can I just delete enough so that the tree width is under control? Then I'll get a better approximation. Right? Okay. Now you face what question? The question you face is, which edges to delete? Here's your exact model, the full model, where if you do, you get exact results on it. You delete some edges, you get this. Right? Here's the problem. And this is the observation is due to Arthur Choi. If you want to make choices of which edges to delete, you probably want to think about it, right? And the problem is you can't think here. Why? Because the original model is too complicated. You can't do inference on it to try to find the edges that have certain properties and so on. So look what Arthur suggested. He said do the other way around. What is the other way around? Do not think about which edges to delete. Go ahead and delete enough so that you get a tree, right? When you do that, what happens? What approximations do you get? Iterative belief propagation, correct? But now you have an approximate model that is easy to do inference on. Now I can think. And then I use it to try to score edges based on their promise or based on how damaging it was to delete them. And then I try to recover those guys that I think will improve the quality of my approximations the most. And this is the recovery part. So relax, compensate, recover. And then the question becomes, well, how do I do that? How do I decide which edge to recover? So I'll show you, I think, 3 heuristics. They vary in their cost. Some of the more sensible ones are costly. And interestingly enough, one of them is very cheap, works pretty well. And I'll show you, it was used in one of the competitions out there, and this did very well. You'll see in just a second. Here's one of the heuristics. What did I do here? I deleted this edge, so I'm ignoring the fact that this and that are equal, correct? I can look at the mutual information between them. Remember what the mutual information is? It's this number that gives you a sense of how independent they are from each other or how dependent. As the mutual information is high, that means they depend on each other. So the idea is you recover which edges that have high mutual information, because these guys are not loosely coupled. Maybe by deleting the edge, you lost a lot. And the intuition is if there are two variables that are loosely coupled, then ignoring the equivalence constraint may not be that bad. Okay, this is basically edge recovery. It's costly. Why is it costly? Because you have to think about it. There's an n square there. You have to look at pairs. And but look at this graph. Look. This is what makes this interesting. This is comparing edge recovery using two methods. This method and random. So look what's happening here. On the x-axis, the number of edges recovered. When I'm here, I recovered all of them. So now it's exact inference, right? This is the error. What we're doing is computing the probability of evidence. In these models, that people call this the Bethe energy. So zero error, this is the most. Look what happens here. This is random. As you randomly recover edges, okay, things get better. But look here. There is a small number of edges that did quite a bit in terms of improving the quality of approximations. And then it kind of starts leveling out, and then again. The observation is there may be a small number of edges. If you find them carefully, they will actually improve the quality of approximation quite a bit, even and without increasing the Treewidth of your model. The other thing you have to realize that's happening here is it's subtle. I have to say it for you to. I'm doing this per evidence. That is, you came and told me what the evidence is, and I'm trying to compute this probability. So the heuristic and what we'll come up with will depend on that evidence. If you try another evidence, to do something else. It is very specific to the query. That's why it ends up being effective. I'm not doing some pre-processing, right? It's happening as you're. Let me give you a couple more, and I would like to make a remark, as I said to some of you who do this. Here's another more complicated thing. I'm going to skip this. I want to tell you about the last one, which is the one used in the competition, which is very cheap. What do you do with this method? You, as we said, you guess these guys initially, maybe, right? Initialize them, and start applying these equations, update equations, correct? Iteration, I have values. Another iteration, let's compute this, until I converge. What you do is, as you're doing this, what happens sometimes is you'll find that some of the edges converge quickly and others give you a hard time. They don't converge. They take long to converge. So the basic idea is those guys that are giving you a hard time, bring them back. Almost no cost. This is a side effect of running the iterations. You're not really doing much work. And actually that worked out pretty well. There was a competition, what was it, 8 years ago at UAI on approximate inference. These were the benchmarks used from different domains. There were 3 queries. PR is probability of evidence, marginals, and MPE. And what is it? There was about 700 networks total. And there was 3 categories, 20 seconds, 20 minutes, and I think 1 hour. You have to produce an answer in 20 seconds. And these are the guys, 2 variants on what I just told you. ED, so the original name for this is EDBP, Edge Deletion Belief Propagation. That was when we started doing this. But what I gave you is the RCR, Relax, Compensate, Recover, which is the more general. The very first version didn't have equivalence constraints. And this is the one discussed in your book. It's a bit complicated. What I described here is the much simpler version. So this guy got the first place for this. So again, look what happened here. Say start. It deletes enough edges, does approximation, and then I immediately have iterative belief propagation approximations. I still have time. It's 20 seconds. Maybe I'm on second 2. Recover edges. Someone comes, 20 minutes, time is up. Okay, here's. It's possible that you stop this algorithm in 2 cases. You run out of time, or what happens? You recover enough edges where exact inference, start choking. Say, please don't bring any more edges. I can barely do it now. Treewidth is like 30. It's usually kind of where it starts getting kind of usual laptop, let's say. So you can yield by saying that's it, I can't handle anymore, or time is up, and it got second place in the other two categories, and also in the 1 hour thing. That's it. The one remark I want to say, and I think I said maybe I have mentioned it to Malika before. If you play this game, you can play it in 2 levels. What I told you, which is domain independent, meaning you tell me I want to do any time approximate inference, right? I want to trade time for quality. And here's a network. I don't know where it's coming from. I want you to come up with a way to do this independent of the domain. This does it, right? The mutual information, the residual recovery, and so on. But it's possible that, let's say, if you're designing codes or you're doing something else, you're doing bioinformatics, or you have a network that has a meaning. It's not an arbitrary network. It is domain specific. Every edge indicates something. It's possible in that case that you may actually find domain specific methods for recovering edges, right, based on their meaning. This game was not played. I hope some of you, I know we come from different backgrounds. It would be rewarding to do that, because if you take a class of models, let's say like we did for genetic linkage analysis, right? This is not a specific network. It's generated from pedigrees and this and that. But I know what the meaning of edges are. And someone says, okay, when I do this using approximate inference, I want to delete the edge that goes from that's trying to copy from this to that. Okay, if you start doing this, then you come up with a new class of algorithm. And you may be able to give guarantees on it that you couldn't do in general. It's a promising direction for approximate inference for those of you who may be interested. All right, guys, I will see you on Tuesday.